All right, electron affinity, by definition, is the energy change when 1 mole of electrons is added to 1 mole of gaseous atoms. So instead of removing electrons, we're trying to add electrons. Some atoms will make that endothermic and some make that exothermic. So the easier it is to gain an electron, the more endothermic it is, and it's actually a negative value for that energy exchange because they're going to give off energy to gain an electron, where other atoms, it's really hard to gain an electron, so it's going to require energy, and those would be positive values. So electron affinity is the energy change when gaining an electron. The values are in section 8 of your data booklet. Again, we don't really do anything with those values though. Electron affinities can be thought of as negative first ionization energies, because if you think about it, it's the opposite of ionization energy. The definition is. The trend, however, is the same. So group 17, which is our halogens, attract electrons easily because they're small, so that effective nuclear charge is great, and that nucleus can attract electrons much easier than, say, group 1 elements. Group 1 elements have the lowest effective nuclear charge, so that attraction is super hard. So as you go towards fluorine, right, I guess we should note that group 18 isn't really discussed because that has a stable full octet. But as you go across a period, you're increasing that effective nuclear charge. And so electron affinity becomes higher. And then as you go down a group, you're increasing the shielding, which makes it more difficult for the nucleus to attract another electron. So it's decreasing. So electron affinity and ionization, they have the same trend on the periodic table, but their definitions are different or opposite. Now, electronegativity can be thought of as the same as electron affinity, but it has a different definition. So the definitions are what makes electronegativity and electron affinity different. Electronegativity, the atom is attracting the electrons in a bond. So if we think about two oxygens bonded together, right, they're sharing electrons, and so electronegativity is that attraction between the atom and those valence electrons. It's related to ionization energy because it's a measure of the attraction between the nucleus and those outer electrons. As you go across a period, it's increasing because you have an increase of effective nuclear charge, right? So that nucleus can attract those electrons easier the smaller the atom is. As you go down a group, because of shielding, the nucleus has a harder time attracting electrons, so it's decreasing as you go down a group. Now, if we look at metals versus nonmetals, remember that there's the stair-step line on our periodic table. This side, the left, are metals, and so those are our blue elements, and then over here we have our nonmetals to the right. And so if you think about it, metals have low ionization energy and low electron affinity and low electronegativity, right? They are the larger atoms on the periodic table. So they lose electrons easily. They have low ionization energy. Nonmetals have high ionization and high electronegativity because they're smaller. So that attraction between the nucleus and those electrons are just stronger. So they gain electrons easily. Remember that francium is the most reactive metal because it's the largest. It will lose the electron easier. Sometimes you can say that it's the most metallic as well. All of that has to do with losing electrons. Gaining electrons easily, we're talking about fluorine, right? We don't normally talk about group 18 because they're not going to form bonds easily. So fluorine is the most reactive nonmetal. It's the smallest nonmetal that can gain electrons. The last trend we have is melting point, and this is something that we don't cover in Chem 1. It depends on both the bonding and the structure. So when we talk about bonding, we're talking about like metals and nonmetals. And then the structure, we're talking about like the size of the atom and what's holding those atoms together. So we look at it in two different ways. We're going to focus on group 1, and then we're going to focus on group 17. So group 1 would represent our metals. The metallic structure is held together by attractive forces between delocalized electrons. So if you remember from Chem 1, metals form metallic bonds, and metallic bonds are held together by delocalized electrons. And so the attraction decreases with distance. And then for group 17, melting point increases as you go down the group. And that's because the molecular structure is held together by London dispersion forces, which is our weakest type of intermolecular force. And it increases, the strength of the intermolecular force there increases as you get larger. So that's why it increases down group 17. So again, you decrease down group 1, but you increase down group 17 for the melting point. You have to look at them as two separate ones. Generally, across the period, you kind of reach a max at group 14, and then you come back down. So it's like you're increasing as you're a metal, and then you start decreasing again when you go to the non-metal side. All right, and then all of our trends, or most of our trends here on the periodic table as a summary: attraction increases, so atomic radius decreases, ionization and electronegativity increase, going from right to left. From left to right, and then the opposite going down. The one that's not listed on here is your melting point. So as you go down group 1, melting point decreases, but as you go down group 17, melting point increases, and that has to do with the forces that are holding our atoms together.